October 29th, 2025, 3I Atlas reached its perihelion, its closest approach to the Sun, and something unprecedented happened. Within hours, telescopes across the world began reporting a surge in brightness that defied every predictive model. Ground-based observatories, solar probes, and even amateur astronomers noticed it, a sudden, disproportionate flash from an object already massive and energetic beyond precedent. For a brief moment, 3I Atlas shone several magnitudes brighter than expected, not because of reflected sunlight alone, but because it seemed to emit light, behaving unlike any known comet. What's strange isn't that it brightened. Comets often do that near the Sun. What's strange is how it brightened, and under what conditions. During perihelion, the Sun was at one of its most volatile peaks in decades, unleashing a series of X-class flares and coronal mass ejections. And one of those bursts, according to heliophysics tracking data, was aimed almost directly at the path of 3I Atlas. At first, scientists thought the timing was coincidence, solar radiation triggering a spike in sublimation, nothing more. But the energy curves didn't match, the spectral response didn't match, even the direction of the outgassing seemed inverted. What looked like a simple cometary reaction began to resemble something far more complex, or far less understood. Tonight, we look at what might be happening inside and around this interstellar traveller, because the more data comes in, the less sense it makes, and it begins with the solar crossfire. When 3I Atlas rounded the Sun, the star was not in a quiet phase. The heliosphere was alive with turbulence, the kind of magnetic violence that makes seasoned space weather researchers uneasy. Between October 25th and October 30th, at least 4 major coronal mass ejections erupted from active regions, AR 3512 and AR 3515, both positioned near the solar equator. Each CME carried billions of tons of plasma at speeds exceeding 2,000 kilometers per second, and the trajectory of one, maybe two, intersected the approximate orbital corridor of 3I Atlas. The timing was uncanny. At 9:40 am UTC on October 29th, the Solar and Heliospheric Observatory logged an X 4.1 class flare that sent a halo CME streaming directly outward. By 1300 Universal Time Coordinated, instruments aboard ESA's solar orbiter captured a diffuse, fast-moving plasma arc extending toward the same heliographic longitude, where 3I Atlas had just passed its perihelion at roughly 1.36 astronomical units. Within 12 hours, photometric monitoring from Mauna Kea recorded a jump in brightness of more than 1 magnitude. Far too large for typical outgassing escalation at that distance. It looked like the object had been struck by the Sun itself. To understand why that's so unusual, it helps to recall how comets normally respond to solar events. A coronal mass ejection can strip volatiles, cause temporary jets, or even fragment a nucleus. But those reactions are short-lived and typically chaotic. The brightness curve of 3I Atlas, however, rose in a steady symmetrical arc, as if it were absorbing energy rather than merely scattering it. The light didn't flare and fade, it glowed and persisted. NASA's Parker Solar Probe, then located about 0.75 astronomical units from the Sun, measured elevated dust plasma densities and anomalous magnetic turbulence around the time of the CME's passage. Some researchers suspect that the interaction region, where the charged particles encountered the interstellar object, could have generated auroral-like excitation on its surface or coma. In other words, the comet might have literally lit up under bombardment, not from heating but from electromagnetic excitation of molecules and metals. Here's where it gets strange. The spectral data obtained from Cerro Tololo and the Very Large Telescope that same night showed emission lines dominated not by water vapour or dust reflection, but by ionized carbon dioxide and nickel, with almost no trace of iron. Normally, a CME impacting a comet enhances standard emission bands of CN, OH, and H2O+, as solar wind drives dissociation of volatiles. Instead, 3I Atlas emitted a set of lines consistent with excited CO2 and neutral nickel, an energy signature seen nowhere else in the solar archives. It's as if the solar plasma had found a resonant frequency unique to this body, exciting specific compounds while leaving others inert. The correlation between the CME's arrival and the brightness increase is tight enough to make some scientists call it causal. The flare's radiation front reached 3I Atlas approximately 8 hours before the densest plasma front, exactly when the visual brightening began. By the time the main plasma hit, the glow intensified further. The behaviour matches what would happen if certain metallic or organometallic materials were photo-excited by extreme ultraviolet radiation, then sustained by continuing charge exchange. In other words, part of 3I Atlas might have acted like a massive phosphor under solar bombardment. That idea, of course, is controversial. The conventional interpretation holds that increased solar energy caused a sudden sublimation of CO2 ice trapped beneath the surface, releasing jets that expanded the coma and reflected more light. But even that doesn't align with the measured decrease in coma radius observed by Hubble and several ground telescopes. The coma shrank while the brightness increased, an inverse relationship that standard sublimation physics can't easily explain. If not dust reflection and not thermal emission, what was the source? Several teams have proposed electromagnetic coupling. When a CME passes a conductive or semiconductive body, it can induce strong transient currents. On Earth, those manifest as geomagnetic storms. On 3I Atlas, a body possibly rich in metals, carbonates, and frozen gases, the same process might have generated internal discharges or surface glows. The interaction between solar plasma and nickel-bearing material could, theoretically, create light emission in specific visible bands without significant heating, a phenomenon observed in auroral arcs and laboratory plasma experiments. But that's not all. Data from the Solar Dynamics Observatory indicated an unexpected shadow-like perturbation in the CME front after its encounter region. Analysts described it as a small but measurable density void, as if part of the plasma had been absorbed or deflected. That effect lasted roughly 90 minutes before smoothing out. The idea that an object of 33 billion tons could create such a disturbance isn't implausible, but the symmetrical nature of the void raised eyebrows. Something about 3I Atlas interacted with the solar plasma in a structured, coherent way, not like an irregular rock breaking up a stream, but more like a magnetic lens. Skeptics argue that it's all coincidence. Solar CMEs are frequent, and with hundreds of objects near the ecliptic, overlap is inevitable. Yet the combination of perfect timing, magnitude increase, and anomalous spectra has turned that coincidence into a statistical improbability. ESA's heliophysics team calculated that the odds of such synchronization by chance were less than 1 in 5,000 for this solar cycle. So the question emerges, was the brightness spike simply an energy transfer, the sun energizing a complex chemical mix, or was 3I Atlas itself somehow predisposed to respond in this peculiar way? The answer matters, because the pattern didn't fade immediately. For nearly 48 hours after the CME impact, the object maintained elevated brightness even as solar output normalized. No known volatile could sustain that level of activity once solar pressure dropped. It's as if the object retained a kind of charge, a stored excitation that decayed slowly over time. A few researchers have drawn comparisons to cometary St. Elmo's fire, a phenomenon once speculated but never observed, electrical discharges caused by solar plasma interaction. If 3I Atlas's surface or internal structure can hold and slowly release electrical energy, that would fundamentally alter our understanding of cometary conductivity and plasma coupling. It would also explain why the light emission spectrum was narrow and consistent instead of chaotic and broadband. Yet, as more data emerged, another layer of strangeness appeared. The emissions seemed to originate from the antisolar side, the hemisphere facing away from the sun. That defies all standard sublimation geometry. It implies that whatever reaction occurred wasn't simple surface heating, but something directional, possibly magnetic or reactive along field lines rather than thermal gradients. This discovery forced observatories to reorient and recalibrate. Some instruments, particularly those on the Solar Terrestrial Relations Observatory, STEREO, detected a subtle tailward jet forming opposite the expected outflow. Within hours, the community was debating whether this was an observational artifact, or the signature of an active magnetic response. That's where the phrase solar crossfire took on a literal meaning. 3I Atlas wasn't merely illuminated by the sun, it was engaged by it, caught between waves of radiation and plasma like a conductor between two electrodes, and instead of disintegrating it brightened, coherently, measurably, and inexplicably. If the flare's energy truly interacted with 3I Atlas in this way, it means we may be witnessing not a passive comet, but an object capable of storing, redistributing, or even modulating solar energy through mechanisms not accounted for in current cometary physics. But that's just the beginning of the problem, because when the data on absorbed radiation and reflected flux arrived, it showed something even more baffling. 3I Atlas shouldn't have survived the encounter at all. At 1.36 astronomical units from the Sun, the expected solar irradiance should have been around 735 watts per square metre. That's a harsh but survivable intensity for most active comets, enough to drive sublimation, but not destruction. The problem is that 3I Atlas didn't just face sunlight, it was struck head-on by one of the most intense bursts of solar plasma activity recorded in over a decade. When the X4 class flare erupted on October 29th, Parker Solar Probe's Fields instrument measured peak particle fluxes exceeding 10 to the 5th protons per cubic centimetre in the inner heliosphere. The corresponding radiation spike was calculated to deliver localized energy densities more than 3 times what any known comet nucleus has previously endured. For most volatile-rich objects, that kind of exposure should have stripped the surface clean, shattered the crust, and left a diffuse debris field. Yet when ground observatories reacquired 3I Atlas, the coma wasn't in chaos. It was smaller, tighter, and unnervingly stable. It's a contradiction that cuts to the heart of why 3I Atlas doesn't behave like anything we know. The energy balance equations simply don't add up. The nucleus, estimated to be roughly 2 to 4 kilometers in diameter, should have absorbed enough energy to heat its outer layers by tens of degrees Kelvin per minute. Even conservative models predict a full sublimation front and massive dust release, but spectral readings from the Subaru telescope tell a different story. A rapid, uniform increase in brightness without corresponding dust signatures. The scattering index remained constant. If the coma didn't expand and if no new material was ejected, then the increase in luminosity must have come from a change in emission, not reflection. That means the energy wasn't producing more dust, it was making the existing material glow. Some heliophysicists have drawn analogies to cathodoluminescence, a process observed when high-energy electrons strike certain crystalline or metallic materials, causing them to emit light. It's the same phenomenon used in electron microscopes to visualize mineral grains. If 3I Atlas's surface contains conductive or semiconductive materials, say nickel compounds or complex organometallic films, intense plasma bombardment could cause persistent luminescence. Theoretically, the surface could act like a vast, slow-decaying phosphor, absorbing charged particles and releasing visible light over time. This explanation, while speculative, aligns disturbingly well with the observed decay curve. After the flare, 3I Atlas's brightness increased by 0.9 magnitudes over 6 hours, plateaued for roughly a day, then decayed exponentially over the next 48. That decay pattern doesn't fit volatile-driven activity, which tends to oscillate with sunlight exposure. It fits the energy release curve of a radiative material slowly returning to baseline after excitation. But there's another layer to this. The radiation environment near perihelion wasn't uniform. The Sun's active regions rotated across its surface, producing alternating bursts of ultraviolet and proton-rich plasma. In that chaos, 3I Atlas somehow maintained stability. Thermal modelling from the University of Helsinki suggests that the surface temperature of its sunward hemisphere likely exceeded 300 Kelvin, while the anti-solar side remained below 120. Any normal comet under those gradients would fracture along thermal stress lines, yet there's no evidence of breakup, fragmentation, or even irregular tumbling. The rotation period, measured from photometric oscillations, remained consistent at approximately 7.2 hours. No torque anomalies, no disintegration signatures. It was as if the object absorbed radiation, redistributed it internally, and re-emitted it as light, a thermally regulated system in an environment where nothing should stay regulated. The question scientists now face is, what is the surface of 3I Atlas actually made of? Laboratory analogues for interstellar ices suggest a mixture of carbon dioxide, carbon monoxide, methane, and silicates embedded in an amorphous matrix. But those compounds can't produce the sustained emission spectra seen in this case. They can scatter or reflect, but they can't emit on their own without ionization. The nickel signal, faint but persistent, provides one possible clue. If the surface includes metallic grains or nickel organic complexes, solar plasma could create transient conductive pathways. Those pathways might dissipate energy through photon emission, not as heat, but as visible light. It's a mechanism rarely considered outside laboratory conditions, because no known natural body in our solar system shows such behaviour. Yet here, we have a potential example on an interstellar object, behaving like a hybrid between a comet and a metallic conductor. Then there's the radiation shadow problem. When the coronal mass ejection reached its densest phase, solar probes detected a temporary dip in particle density trailing the object, a partial wake that persisted for more than an hour. That implies absorption or deflection on a scale disproportionate to the comet's mass. The simplest way to explain that is by invoking an induced magnetic field. If 3I Atlas carried even a weak internal magnetic structure, the incoming plasma could have wrapped around it, creating a magnetospheric bubble, a sort of protective sheath. It's not unprecedented. Rosetta's measurements of Comet 67P detected weak magnetic coupling, but the strength required to carve a wake visible at millions of kilometers is immense. For that to happen, the body would need either high electrical conductivity or a composition capable of supporting sustained induced currents. And that takes us back to the nickel. Nickel, when alloyed with certain elements or embedded in organics, forms compounds with unusually high conductivity under ionizing radiation. The detection of nickel without iron, confirmed independently by multiple observatories, may not be a coincidence. It might be the signature of a specific material class, one that reacts strongly to radiation, stores charge, and re-emits it as light. Of course, not everyone agrees. Critics warn that overinterpreting spectral anomalies risks slipping into science fiction. They point out that early data from interstellar objects like Oumuamua also seemed inexplicable until more mundane explanations, elongated shape, non-gravitational acceleration from outgassing, were proposed. But this case is different. 3I Atlas isn't accelerating. Its orbit remains consistent with gravitational predictions. The anomaly isn't motion, it's luminosity. And luminosity is data we can measure directly without inference. Still, the simplest possibility can't be ruled out, that the flare simply triggered a deep-buried reservoir of CO2 under pressure, releasing a rapid jet that momentarily boosted brightness. Yet if that were the case, we'd expect the coma to expand dramatically, which it didn't. Instead, the coma contracted and intensified, as if the energy was trapped and focused inward. One European team, analysing photopolarimetric data from the Bernard-Liot telescope, proposed that electrostatic cohesion might have compressed the dust cloud. Under high radiation and plasma flux, charged grains could experience attractive forces rather than repulsion, forming denser, darker clusters that paradoxically reflect more total light per unit area. In other words, radiation could have compacted the coma instead of dispersing it, explaining both the shrinkage and the brightening. But that would require an immense charge density, far beyond anything observed on a comet before. All these models converge on a single unsettling conclusion. Whatever 3I Atlas is, it interacts with radiation differently than ordinary matter. It doesn't scatter, it responds. If confirmed, that interaction might mean we're not just witnessing a chemical reaction, but an electromagnetic one, a coupling between solar plasma and an object whose properties border on the engineered or the exotic. Some researchers whisper comparisons to interstellar debris or techno-signatures, though no one dares publish those words yet. The journals demand repeatable data, but the numbers don't lie. The radiation flux should have destroyed it. Instead, it thrived, and when spectrometers began resolving the composition of the light, another clue emerged, one that pushed the discussion from the energetic to the chemical. Nickel and iron are cosmic twins. They're forged side by side in stellar furnaces, born together in supernovae, fused from the same collapsing cores. Wherever we find one, we find the other, locked in almost perfect ratios. Asteroids, meteorites, planetary cores, even the faint dust drifting through interstellar clouds all obey this rule. So when 3I Atlas began emitting clear nickel lines, while iron lines remained flatlined at zero, it sent a shiver through the spectroscopy community. The first hint came from Cerro Tololo's mid-resolution spectra, taken just after the flare impact. Between 340 and 380 nanometers, the absorption bands that normally mark VI were conspicuously absent. Instead, narrow emission peaks at 349, 351, and 356 nanometers lit up, signatures of neutral nickel transitions first catalogued in laboratory plasma experiments, not in comets. At first, analysts blamed instrumental noise. but a day later the same pattern appeared in data from the Nordic Optical Telescope, then again from the VLT's X-Shooter instrument. Different hemispheres, different detectors, same signal. The ratio of nickel to iron abundance was at least 40 times higher than anything seen before. That's not a statistical outlier, it's a new category. To visualize how strange this is, consider that comet 67P, measured by Rosetta, carried nickel and iron in near equal parts, both locked in refractory dust grains. The nickel there required the spacecraft's mass spectrometer to even detect it. But with 3I Atlas, the nickel was glowing, emitting on its own, freely excited, apparently gaseous. If true, that means solid metal compounds somehow vaporized and ionized under solar bombardment, yet iron, more volatile under similar conditions, did not. No existing thermal model explains that separation. Nickel's sublimation temperature is roughly 1728 Kelvin. Iron's is 1811. Their thresholds are close enough that any heating capable of releasing one should free the other as well. The data suggests selective excitation, something filtering one element while energizing the other. ESA's solar orbiter provided a clue. During the same window, its SPICE spectrometer recorded an unusually strong ultraviolet flux at 117 nanometers, overlapping with known nickel-ion absorption cross-sections. In plain terms, the radiation storm that hit 3I Atlas was tuned to nickel's resonance frequency. That coincidence might sound trivial, but resonance matters. When photons strike atoms at just the right energy, they lift electrons efficiently, producing luminous emission with minimal heating. If 3I Atlas's surface carried nickel-rich films or salts exposed by earlier outgassing, the CME could have excited those directly, lighting them up while leaving nearby iron inert. But there's a deeper question. Why does the object have nickel without iron in the first place? Some researchers point to exotic condensation processes in other stellar systems. In metal-poor nebulae, localized magnetic fields can cause fractionation, separating elements by ionization potential during dust formation. Nickel, slightly less magnetic than iron, could have condensed independently. If 3I Atlas originated in such a region, its chemical fingerprint would naturally diverge from solar system material. That would make it not just interstellar in trajectory, but chemically alien in origin. Others, more cautious, suggest a measurement artifact. Perhaps iron lines were suppressed by overlapping molecular bands, or masked by the brightness of CO2 emissions. Yet repeated high-resolution scans corrected for that possibility, and still found nothing. The iron signal simply wasn't there. The implications ripple outward. Nickel alone can act as a catalyst in complex carbon chemistry. Under bombardment, it can form transient organometallic compounds, nickel carbonyls, that absorb energy and emit strongly in the visible spectrum. Nickel tetracarbonyl, for example, forms when CO gas meets metallic nickel under moderate pressure and heat. It's unstable, toxic and volatile, and it glows faintly when decomposing under UV radiation. If 3I Atlas's CO, too rich coma contained trace CO and reactive nickel surfaces, the CME could have sparked precisely that chemistry. Imagine a vast invisible laboratory drifting through space. The sun provides the energy, nickel acts as the catalyst, carbon dioxide becomes the reagent. For a few hours an interstellar reactor ignites, producing a radiative haze far brighter than sublimation alone could achieve. Then, as the plasma subsides, the reaction quenches, leaving no trace but the spectral ghost of nickel. To most astronomers, that scenario sounds speculative, but speculation is what the data demand. The same spectral peaks persisted through multiple observation cycles before fading gradually, not abruptly. That slow fade matches chemical recombination, not ballistic ejection. It suggests that whatever process produced the nickel glow happened repeatedly across the surface, not from a single jet. And there's the spatial element. Polarimetric imaging from La Palma revealed a faint asymmetry, nickel emission stronger on the anti-solar side, the same direction as the mysterious jet detected earlier. That alignment hints at a coupling between chemical excitation and magnetic orientation, as though charged particles spiraling along field lines triggered localized nickel reactions. NASA's spectroscopic data, however, remains conspicuously absent. The Mars Reconnaissance Orbiter and the James Webb Space Telescope both had line-of-sight windows during the event. No releases, no spectra. Meanwhile, ESA's team made theirs public within 48 hours. It's led to a quiet unease in the research community, a sense that something unusual was seen, but not yet ready for peer review. Still, the nickel anomaly is undeniable. Whether chemical or electromagnetic, it suggests that 3I Atlas's surface is not an inert crust of ice and dust, but a reactive interface, one capable of selective, perhaps even self-sustaining emission. Some physicists have begun to frame it as a kind of radiative battery, solar energy in, photon energy out, mediated by exotic compounds. It would explain why the object survived radiation overload and why its glow decayed so slowly afterward. If that's the case, then what we're witnessing isn't a coincidence of chemistry, it's a property of design. Not deliberate design necessarily, but structural design at a molecular level. A surface tuned by cosmic evolution to interact with radiation efficiently, like the skin of a living organism adapted to stellar light. Skeptics recoil from that analogy, yet even they admit something about 3I Atlas violates equilibrium. The universe loves balance, iron and nickel, heat and radiation, input and output. But here, balance is gone. One element sings while its twin remains silent. One side of the comet brightens while the other dims. Even its orbit, nearly locked to the ecliptic plane, mirrors the organised precision of a solar system body rather than the randomness of an interstellar wanderer. No single anomaly proves anything, but stacked together, the timing, the brightness, the nickel line, it paints a pattern of deliberate complexity in a place where chaos should rule, and the polarization data only deepens the mystery. Because when astronomers measured the way light scattered from 3I Atlas's coma, they found an effect so strong it bordered on impossible. Negative polarization far beyond known limits, as if the light itself were being twisted before leaving the dust. When astronomers speak of polarization, they're talking about the orientation of light waves, how they oscillate as they travel through space. Dust, gas, and reflective surfaces polarize light in predictable patterns. For decades, cometary polarization curves have followed a simple rule. As sunlight scatters off dust particles, polarization increases with phase angle, the angle between the sun, the comet, and the observer. Around 20 degrees, the polarization usually becomes slightly negative, a minor dip caused by backscattering. It's gentle, fleeting, and rarely exceeds -2%. But 3I Atlas broke that rule completely. On October 30th, less than 24 hours after its brightness surge, 3 observatories, the Bernard-Liot telescope in France, the Crimean Astrophysical Observatory, and the Haida Polarimetric Array in Japan, reported negative polarization values approaching -10% at phase angles where no comet has ever shown such behavior. For comparison, even the most anomalous comets in history, like 17P/Holmes after its 2007 explosion, only reached -4%. Something about 3E Atlas was twisting light in ways that ordinary dust physics cannot explain. At first, researchers suspected instrumental error. Polarimetry is notoriously sensitive. A misalignment of even a few arc-seconds can produce false readings. But when independent teams confirmed the data within hours of each other, the consensus shifted. The measurements were real. The object was scattering light differently than anything we've seen in the solar system. The magnitude of that negative polarization implied that photons weren't merely bouncing off dust. They were being absorbed and re-emitted with a phase inversion. That's not how cometary dust behaves. It's how certain engineered metamaterials behave, substances structured at microscopic levels to manipulate electromagnetic waves. Of course, no one is claiming 3I Atlas is artificial, but its surface, whatever it's made of, behaves like a coherent optical medium rather than a chaotic one. Let's unpack what that means. Light polarization depends on the size, composition, and geometry of scattering particles. In ordinary comets, those particles are irregular silicate grains and carbonaceous clumps, messy, random, light-scattering machines. But for polarization to invert this strongly, the particles must be uniformly aligned, layered, or electrically charged in a consistent orientation. Something must have organized them. Coincidentally, or perhaps not, the period of strongest negative polarization overlapped precisely with the anti-solar jet event. The direction of that jet observed tailward from the Sun matched the axis of polarization rotation. In other words, the light twisting occurred along the same vector as the mysterious outflow. ESA's solar orbiter and the Stereo probe captured indirect evidence of magnetic structuring in that region, a ripple in the interplanetary magnetic field that appeared synchronous with the flare's impact and the comet's response. If those field lines wrapped around 3I Atlas, they could have aligned charged dust grains like iron filings around a magnet. Except, of course, there's no iron. Which raises the obvious question, what kind of dust can align itself magnetically without iron? Nickel might be the answer again. While less magnetic than iron, nickel compounds can still align under strong fields, particularly if coated with carbonates or oxides. And with the sun's HSME pumping plasma currents through the coma, those grains might have self-organized into sheets or filaments, microscopic antennas reflecting and re-emitting light coherently. This would explain not just the polarization, but the spectral consistency. The coma acting like a dynamic mirror of ordered filaments vibrating in unison. Some scientists have dubbed it the photonic web, a poetic but fitting description for what might have been a transient electrically structured atmosphere around the object. However, one problem persists: polarization. This strong implies coherent scattering, meaning the waves stayed synchronized across distances far larger than the individual grains. To produce that, the structure must have extended hundreds, maybe thousands of meters, a scale suggesting that the coma itself temporarily behaved like a single optical system. That's almost impossible under known physics. Dust and gas should randomize light within nanoseconds. Yet the data shows persistent, stable inversion for nearly 6 hours, fading only as the CME dissipated. A team from the University of Padua proposed a daring model that 3I Atlas briefly generated an induced magnetic sheath, a quasi-magnetosphere, trapping charged particles in looping currents. These loops, in turn, produced a network of aligned filaments, tiny lightning paths frozen in the plasma wind. As sunlight struck them, it scattered through multiple layers, each slightly out of phase, producing destructive interference in one polarization direction and constructive in another. The result? Light twisted backward, inverted, and polarized negatively. This isn't entirely unprecedented. Laboratory plasma experiments at Sandia National Laboratories have produced similar polarization inversions in controlled magnetic confinement fields. But in nature, acometry scales. Never. Critics argue that the readings might still be contaminated by the sun's own polarization shifts during flares. Solar light, after passing through coronal plasma, can pick up complex polarization states. Yet the pattern here was local, rotating with the comet's orientation, not the sun's. And when 3I Atlas drifted a few degrees farther from the flare's direct line, the polarization snapped back toward normal levels. It's difficult to overstate how unsettling this result is to comet scientists. Polarization isn't a trivial detail, it's a fingerprint of physical structure. A polarization of negative 10% implies an organized geometry in the coma, something smooth, coherent, and highly reflective at specific wavelengths. That shouldn't exist around an interstellar ice ball being bombarded by plasma. It's like seeing a perfect mirror form out of smoke, yet this mirror appeared, reflected light the wrong way, and then dissipated as if it had never been there. Some astrophysicists are quietly suggesting that 3I Atlas may possess a surface layer capable of self-assembly under energy stress, perhaps nanoscale conductive grains that align electrostatically when charged. Others think it's evidence of a highly porous structure that traps and diffracts light in complex ways, producing negative polarization as a byproduct. But both camps agree this isn't normal scattering, it's structured interaction. And there's another unsettling connection. The region of strongest polarization coincides spatially with the area emitting the nickel lines. That means the same zone responsible for the spectral anomaly also generated the light-twisting behavior. The chemical and optical anomalies are likely linked, perhaps two symptoms of one deeper phenomenon. Whatever that is, it doesn't behave like dust, gas or metal as we know them. It behaves like something intermediate, an electrically responsive, radiatively active medium. By now, the scientific community was split into two camps. One saw 3I Atlas as a bizarre but natural outcome of interstellar chemistry, its strangeness a product of alien formation environments. The other began to whisper, not publicly but in private correspondence, about plasma confinement, coherence, and patterns too regular to ignore. But before anyone could draw conclusions, another observation shattered the debate. because just as telescopes adjusted to track its brightening coma, something even stranger appeared, a narrow focused jet, but not pointing toward the sun as physics predicts. It was firing in the opposite direction. The first report came from the Atacama Large Millimeter Array on October 30th, just hours after the flare-induced brightening. Using interferometric imaging, astronomers detected a faint but distinct plume of material extending not outward, but inward, toward the solar direction. Within minutes, the data was double-checked by independent teams using the Solar and Heliospheric Observatory's LASCOC3 coronagraph. The images confirmed the impossible, an anti-solar jet, narrow and collimated, stretching tens of thousands of kilometers sunward. At first, observers thought it was a processing artifact, a misaligned background subtraction, or a flare reflection. But time-lapse imagery showed motion. The plume was dynamic, pulsating, releasing bursts of material at regular intervals, and its geometry was shockingly precise, a straight, confined jet instead of the broad diffuse fans common in cometary outgassing. This one looked controlled. In ordinary comets, jets occur when sunlight heats a patch of volatile ice, creating local gas pressure that vents outward. Because solar radiation pushes dust and gas away, those jets always bend in the anti-solar direction. Even when irregular rotation causes odd angles, the resulting tails eventually realign away from the sun. The radiation pressure is relentless. To maintain a sunward jet under those conditions, something would have to overpower the solar wind, or ignore it completely. And that's the enigma. 3. Atlas's sunward jet persisted for nearly 12 hours, oscillating slightly as if modulated by rotation. Its velocity, measured by Doppler shift, reached an astonishing 200 meters per second, fast enough to expel material, but not so fast as to suggest explosive eruption. It was steady, measured, rhythmic. Some astronomers theorized it could be a backflow jet, material that had first vented from the night side, curved around by magnetic field lines, and redirected toward the sun. But the curvature wasn't there. The jet emerged directly from the sun-facing hemisphere. Others proposed a more radical idea: electromagnetic confinement. If the nucleus carried an induced magnetic field, as hinted by the CME wake anomalies, then ionized gases could be guided along those field lines. Under certain conditions, plasma trapped in magnetic loops can stream both toward and away from the sun, much like solar prominences do. In that sense, 3I Atlas might have acted not as a passive object, but as a temporary plasma node in the heliosphere, generating its own localized currents. That concept gained traction when data from the solar orbiter's magnetometer showed a sudden symmetrical perturbation in the interplanetary magnetic field near the object's position. The field lines appeared to bow inward toward 3I Atlas for nearly half an hour before relaxing. The signature resembled a magnetic reconnection event, the same kind that powers solar flares, only on a vastly smaller scale. If true, this would mean 3I Atlas briefly generated a magnetic loop connecting directly to the solar field, a literal tether between an interstellar object and the sun. The anti-solar jet could then be interpreted not as gas venting, but as plasma streaming along that loop, guided by electromagnetic forces rather than radiation pressure. The chemistry supports the idea. Spectroscopy of the jet region revealed faint nickel and carbon lines, the same compounds implicated in the earlier luminosity anomalies. Those materials are conductive, capable of carrying current and sustaining glow discharges under plasma exposure. Combined with the object's apparent ability to retain charge from the CME bombardment, the sunward jet might have been the result of electrical equalization, a slow release of accumulated potential back toward the sun. In essence, 3I Atlas may have been discharging. Such an idea isn't entirely new. Plasma physicist Anthony Perrott once proposed that certain cosmic bodies could behave as electrical double layers, storing charge differentials between internal and external plasma sheaths. When the potential difference becomes large enough, the system discharges along field lines, producing jets, arcs, or filaments. It's a fringe hypothesis when applied to comets, but here the data almost demands it, and yet the sunward jet wasn't destructive. No fragmentation, no sudden drop in brightness, no signs of erosion. In fact, the nucleus remained photometrically stable. Whatever was happening, it was controlled, efficient, and non-explosive. The emission faded gradually as the solar wind normalized, as though the system had rebalanced. What disturbed scientists most was its symmetry. The jet didn't emerge from a random patch but from a fixed point aligned with the object's rotation axis. That alignment hints at structural consistency, perhaps a vent, fissure, or magnetic pole. If so, 3i Atlas might possess a stable geometry, something persistent enough to orient its interactions predictably with the Sun. It's a kind of order rarely seen in natural comets, which tend to spin chaotically and shed matter irregularly. 3i Atlas seemed coordinated. When modelling teams ran simulations of the observed jet dynamics under realistic radiation pressure and plasma flow, none could reproduce the trajectory. Even assuming heavy molecular mass and low particle charge, solar wind should have bent the stream backward within minutes. Instead, the jet maintained its shape for hours. One researcher at the Max Planck Institute summarized the situation bluntly. Either the material leaving that body is not subject to the same electromagnetic forces as normal plasma, or the body itself is generating a counterfield strong enough to resist the Sun. Neither possibility sits comfortably in standard comet physics. If the first is true, that the emitted material behaves differently, then we're looking at chemistry unlike anything found in our solar system. Perhaps the particles are neutral aggregates of carbon dioxide and nickel clusters, resistant to charge separation. If the second is true, that the object generated its own counterfield, then 3i Atlas may have an interior conductive framework capable of sustaining induced currents large enough to shape plasma behavior across tens of kilometers. No one can say for certain. But the timing of the event fits perfectly with the CME aftermath, about when a charged body, having absorbed massive energy, would begin to discharge. It may have been the final echo of the solar encounter, an object briefly acting as an extension of the Sun's own electrical system, then falling silent. After the jet subsided, telescopes observed a new effect. The coma, instead of expanding as expected, began to contract. Its diameter shrank by nearly 30% over 2 days, concentrating brightness even as the energy input from the Sun decreased. For an object that had just expelled matter, the reaction was paradoxical. Comets normally shed mass and expand. 3i Atlas seemed to compress. And that leads to the next mystery, perhaps the strangest of all, how a shrinking coma can grow brighter in defiance of every physical model. By November 1st, the global network of observatories tracking the object reported a steady contraction of its visible envelope. The coma's apparent radius decreased from nearly 45,000 kilometers to just under 31,000 in less than 48 hours. Yet photometric readings showed its integrated brightness climbing, not falling. That single contradiction forced analysts to stop, recalculate, and then stop again, because no equation in classical cometary physics could reconcile a shrinking coma with a rising luminosity. Normally, when comets near the Sun, heat causes volatile ices to sublimate, gas escapes, dust follows, and the coma, a vast halo of particle, blooms outward. When sublimation slows, the coma fades and expands into the void. But 3i Atlas was doing the opposite. After releasing its strange sunward jet, it appeared to compress its atmosphere as though the gases surrounding it were being pulled inward or magnetically trapped. Telescopes that specialize in high-resolution imaging like the VLT and Subaru caught it in astonishing detail. Faint filaments of dust curving back toward the nucleus, as though drawn by invisible lines of force. The structure resembled something between a funnel and a cocoon, a pattern never before documented around a comet. To make sense of it, astronomers turned to models of plasma confinement. In a highly charged environment, if the coma's dust and gas become partially ionized, electromagnetic fields can influence their motion. If 3i Atlas retained a residual magnetic field after the CME impact, even a transient one, it could theoretically corral ionized particles back toward its surface. This would cause the coma to tighten, compressing both gas and dust. That hypothesis gained weight when the European Space Agency's solar orbiter recorded a small but measurable drop in local plasma density trailing the object. Something was absorbing charged particles from the solar wind, acting almost like a sink rather than a source. In effect, 3i Atlas may have been inhaling the surrounding plasma. If true, that would flip the cometary paradigm on its head. For centuries, comets have been defined as objects that emit material, frozen reservoirs that sublimate and shed. but 3I Atlas might be the opposite, a body that absorbs and reorganizes matter under specific conditions. The brightness spike during contraction offered another clue. Polarimetric readings indicated that the emitted light became increasingly coherent, less scattered, more unified, as the coma shrank. That means the material wasn't simply condensing physically, it was aligning optically. Dust particles appeared to orient themselves, forming regions that reflected and re-emitted light, almost as if part of a single surface. Imagine a cloud of dust where every grain turns the same way, reflecting sunlight in phase. The result would be a brighter, more focused glow, even as the cloud becomes smaller. This phenomenon, while never seen in nature at this scale, mirrors behavior observed in laboratory plasmas known as dusty plasmas, systems of micron-sized particles suspended in electric fields. In those experiments, dust grains spontaneously form lattices or shells under electrostatic attraction, behaving like ordered crystals. 3I Atlas's coma, it seems, was doing something similar, a colossal, self-organizing dust crystal in space. The implications are extraordinary. If such a process is real, it suggests that the comet's surrounding environment was actively structured by electromagnetic interactions. Instead of a chaotic, expanding gas cloud, it may have formed a bounded plasma sheath, a double layer where electrons and ions separate, creating confinement and order. Within that sheath, radiation could be trapped, scattered, and re-emitted with high efficiency. In simple terms, the coma became a luminous shell. This could explain why the object brightened even as its volume decreased. The confined plasma would have increased in density, enhancing collisional excitation and amplifying its glow. It's a mechanism closer to that of a low-pressure gas discharge lamp than a comet. The sun provided the current. The coma acted as the bulb. Skeptics proposed more conservative explanations. Some suggested that optical illusions caused by phase angle effects might make the coma appear smaller while maintaining brightness. Others argued that a forward scattering geometry, when light bounces off dust in the observer's direction, could mimic increased luminosity. But these theories fell apart under precise measurements. The shrinking was measurable in all directions, and the polarization curve shifted toward alignment rather than scattering. In short, the coma was physically contracting. The most striking evidence came from spectral broadening, or rather the lack of it. When gases contract or expand rapidly, their emission lines spread due to Doppler effects. Yet 3I Atlas's spectral lines remained narrow and stable. That indicates uniform motion, material moving cohesively, not chaotically. One intriguing interpretation emerged from a collaboration between the Finnish Meteorological Institute and Kyoto University. The coma might have been under negative electrostatic pressure. In a charged plasma, opposite polarities attract, and if the electric field around 3I Atlas reversed, perhaps after the antisolar jet discharged its positive charge, it could have drawn the remaining plasma back inward. The result would be a temporary collapse as particles rushed to neutralize the field imbalance. If that happened, the energy released during recombination could account for the sustained glow. When ions and electrons reunite, they emit photons, light born directly from electrical neutrality restoring itself. Such recombination events are short-lived on Earth, but in the near vacuum of space they can last far longer. If 3I Atlas's coma acted as a confined plasma shell, recombination light might have radiated for hours, even days after the CME passed. There's also an exotic chemical possibility. When CO2 ice interacts with plasma and metallic catalysts, like nickel, it can undergo partial reduction, forming complex carbon compounds. Some of these, such as nickel-carbonyl clusters, exhibit photoluminescence. If those reactions occurred as the coma collapsed, chemical energy could have contributed to the brightness spike. That, in turn, could explain the strange spectral continuity between the nickel lines and CO2 bands, two elements reacting together under energy stress, releasing photons as byproducts of recombination. Whether electromagnetic or chemical, the collapse revealed something crucial. 3I Atlas was active in a way that normal comets are not. Its coma didn't just react to sunlight, it interacted with it, restructuring itself under changing conditions. In a sense, the object was performing feedback, absorbing energy, transforming it, and releasing it back in controlled bursts. It was less like a rock evaporating in space, and more like a system, a dynamic entity balancing its own internal and external energy flows. One researcher at the European Southern Observatory put it bluntly during a post-perihelion briefing: "We're not watching a frozen relic behave badly. We're watching a process, something that regulates itself, and that regulation seemed tied to its unusual chemistry, particularly its overwhelming abundance of CO2 compared to water, a ratio that defies the norms of any known comet. Because as the coma shrank, the spectral data made one thing clear: there was almost no water vapor at all. In early November, after the coma collapse stabilized, infrared spectrometers across multiple observatories converged on one puzzling finding. 3i Atlas was venting carbon dioxide almost exclusively. The expected water emission bands at 2.7 microns were faint, nearly drowned out by the overwhelming CO2 peaks at 4.26 microns. By every metric, the object's volatile inventory was inverted. In ordinary comets, water is the primary driver of activity. CO2 and CO are secondary gases that emerge deeper into the heating phase. But here the ratio was backwards, at least 5 times more CO2 than H2O, perhaps more. To most cometary physicists, that's not just strange, it's a red flag. It means that 3i Atlas isn't behaving like anything formed within the Sun's protoplanetary disk. Water ice dominates bodies born in our system, because hydrogen and oxygen were abundant in the early nebula. Carbon dioxide requires a colder, more carbon-rich environment to condense, so a CO2-dominant composition implies formation in an entirely different chemical regime, maybe near a carbon star, or deep within the outer zones of a primordial molecular cloud where water never condensed efficiently. But that's just the start of the problem. When the object reached perihelion, the heat flux should have triggered runaway sublimation. CO2 sublimates at around 80 Kelvin. The surface temperature at 1.36 astronomical units was estimated near 250 Kelvin, more than enough to blow off vast amounts of gas. Instead, gas production rates remained moderate and stable. The emission was strong, yes, but steady, as if pressure was being regulated internally. The ratio of CO2 to H2O wasn't just high, it was consistent. Normally, as a comet rotates, active regions produce variable emissions. Spectral curves fluctuate every few hours. 3i Atlas, however, maintained a uniform signal for days. That steadiness hints at a globally distributed reservoir, or, more provocatively, a mechanism that controls its release. One hypothesis suggests that the surface is coated in a carbonaceous crust, a kind of refractory blanket that suppresses water sublimation while allowing CO2 to leak through microfractures. The pressure from trapped carbon dioxide might percolate through the matrix, emerging in uniform flow, yet even that can't explain the observed brightness and chemical isolation. Another theory, far more radical, proposes that 3i Atlas's CO2 isn't entirely frozen at all. Some of it might exist as clathrate structures, gas molecules trapped in crystalline cages of other compounds. Under ionizing radiation, these clathrates can release CO2 gradually, maintaining steady emissions even under fluctuating temperatures. If so, the object's stability would make sense. It would behave less like ice melting, and more like a regulated reactor releasing gas through microscopic valves. Still, the chemical ratios remain unearthly. Spectrometers on the IRTF and Subaru recorded subtle features at 4.27 and 4.28 microns that don't correspond to pure CO2. They suggest the presence of carbonyl compounds, potentially nickel carbonyl, Ni open parenthesis CO close parenthesis 4, the same organometallic complex hinted at in earlier spectra. That discovery startled chemists because nickel carbonyl is not just rare. It's almost impossible to form naturally without precise conditions. Metallic nickel, high CO pressure, and energy input from radiation. All three existed near perihelion. If those reactions were real, it would explain the comet's persistent glow and unusual chemistry simultaneously. The formation and breakdown of nickel carbonyl could provide a self-sustaining feedback loop. CO2 decomposes under solar radiation, reacts with nickel to form NiCO4, then photodissociates again, releasing photons and regenerating CO2. The process would recycle both elements while emitting visible light, an elegant, if bizarre, natural oscillator. It's chemistry on a planetary scale, something more akin to a catalytic surface than an inert rock. This could also clarify why the coma's spectral composition remained uniform. The reactions occur at the surface level, not in isolated vents. The entire sunward hemisphere could act as a photochemical interface, converting solar energy directly into chemical luminescence. For astrophysicists accustomed to inert ice balls, this idea is uncomfortable. It blurs the line between geology and chemistry, between object and process. 3I Atlas seems less like a passive relic from another system and more like a reactive system, a body that transforms energy through structured mechanisms rather than random outgassing. But the implications reach beyond chemistry. A CO2-dominated composition also changes how the object interacts with radiation. Carbon dioxide absorbs strongly in the infrared, trapping heat. That could explain why the nucleus didn't fragment despite the flare barrage. Instead of surface evaporation, the energy may have been absorbed and redistributed through CO2 re-emission, effectively cooling itself by radiating away excess energy. It's a primitive form of thermal regulation, one that mimics engineered radiative balance. The lack of water vapor also tells us something about its past. Water is fragile. It's easily lost during long interstellar journeys as cosmic rays and ultraviolet light strip molecules apart. CO2, by contrast, is more robust. If 3I Atlas spent millions of years drifting through the interstellar medium, its water could have been destroyed while carbon dioxide survived. What we see now might be the chemically weathered shell of an ancient body stripped of its lighter volatiles, leaving behind a dense CO2-rich residue. Yet there's a catch. Even interstellar radiation can't completely eliminate water without leaving traces of its photolysis, hydroxyl emissions, oxygen, hydrogen lines. None were found. It's as if water never existed on 3I Atlas to begin with. That makes its origin even more exotic. It could have formed in a carbon-rich, oxygen-poor protoplanetary disk, a region where the chemistry favoured CO2, methane and nickel compounds over H2O. Or, perhaps more intriguingly, it might have condensed in the outer envelope of a dying star, a place where carbon dominates and metals like nickel form complex molecules in cooling gas. If so, 3I Atlas isn't a comet at all in the traditional sense. It's a fragment of a planetary system that never resembled ours. And if that's true, its arrival here offers more than curiosity. It's a sample of alien chemistry entering the solar system for the first time. But its orbit complicates that narrative, because despite being an interstellar object, 3I Atlas moves almost perfectly along the solar system's ecliptic, the plane where planets orbit. That alignment is statistically improbable for a random interstellar visitor. It suggests something deliberate about its trajectory, or at least something guided by forces we don't fully understand. When 3I Atlas was first catalogued, its inclination immediately caught attention, barely 1.4 degrees relative to the ecliptic. For context, that's flatter than the orbit of Mercury. By interstellar standards, it's absurd. Out of all the infinite directions from which an object could enter our system, 3I Atlas approached along the narrow disk where every major planet resides, the same plane that defines our solar architecture. Statistically, the odds are remote. Calculations from the Harvard-Smithsonian Center for Astrophysics estimate that only about 0.01% of random interstellar trajectories would align this closely with the ecliptic. It's a cosmic bullseye, as though something guided the approach. The last confirmed interstellar objects, Oumuamua in 2017 and 2I/Borisov in 2019, came in at steep angles, 123 degrees and 44 degrees relative to the plane of the planets. That's what we expect. Interstellar debris enters from arbitrary orientations following the galactic random. But 3I Atlas broke that pattern completely. Its path didn't just skim the ecliptic, it rode it. Initially, researchers called it coincidence. After all, the ecliptic represents a vast surface area. The chance of a lucky alignment, while small, isn't zero. But the more data accumulated, the stranger it looked. The object's velocity vector, 215,000 km per hour, was nearly parallel to the planetary disk, crossing it like a commuter on a known highway. It's almost as if the object wasn't just entering the solar system, it was navigating through it. Even more curious is its perihelion distance, 1.36 astronomical units, squarely between Earth and Mars. That's not a deep solar dive like typical comets, nor a distant skim through the outer system. It's the sweet spot for maximum solar energy absorption while avoiding destructive tidal forces. In other words, it's an optimal trajectory, the kind you'd pick if you wanted to survive a close solar pass without disintegration. Such precision has revived a familiar debate in the scientific community. the same one sparked by Oumuamua years ago? Are we witnessing an engineered trajectory or a natural fluke? To answer that, we need to understand what alignment really implies. Objects entering from interstellar space are influenced primarily by the sun's gravity. As they fall inward, their paths are hyperbolic. Open, one time passes through the solar system. But for 3I Atlas to enter along the ecliptic, its original approach vector relative to the sun must have already been within a few degrees of that plane. That suggests it wasn't just falling randomly through space. It came from a region moving roughly parallel to the sun's own orbital plane within the galaxy. That on its own is improbable. But then there's the matter of velocity. Most interstellar debris travels at speeds between 20 and 60 kilometers per second relative to the sun. 3I Atlas clocked in at nearly 60 kilometers per second exactly at perihelion, not excessively fast, not unusually slow, but precisely at the threshold that allows maximum solar capture for observational study. It's a Goldilocks speed, fast enough to confirm its interstellar origin, slow enough to stay visible for weeks. For astrophysicists trying to model the object's past, this creates a headache. Tracing its orbit backward through galactic coordinates shows no clear origin point. It doesn't align with any known star's path, no recent supernova debris, no molecular cloud drift. It's as though it emerged from interstellar space already moving in sync with the solar plane. One hypothesis suggests gravitational pre-alignment. If the object passed near a massive body, perhaps a rogue planet or stellar remnant, before entering our system, its velocity vector could have been deflected into ecliptic alignment by chance. But the precision required borders on the absurd. The slightest deviation would have tilted it by several degrees, easily noticeable. Another theory, more speculative but mathematically elegant, posits that 3I Atlas could have been influenced by the galactic magnetic field. Charged dust and small conductive bodies can, over time, align their motion with large-scale magnetic currents. If 3I Atlas carries residual charge or metallic inclusions, it might have drifted through the Milky Way, surfing magnetic gradients that coincidentally run parallel to the solar ecliptic. That's poetic, but it still doesn't explain the near-perfect match to planetary motion. Magnetic alignment could orient it broadly, not to within fractions of a degree. At this point, the story takes a subtle turn, because when scientists at ESA plotted the object's exact node, the point where its path crosses the ecliptic, they realised something disquieting. That node lies very close to the orbital longitudes of Earth and Mars during late October. In other words, 3I Atlas's plane intersected the solar system's two most observationally convenient vantage points. Both Earth-based and Mars-based instruments had line-of-sight access during perihelion. If this were coincidence, it's an extraordinary one. For the agencies tasked with studying the object, it was an observational blessing. But for theorists, it raised questions. Why does an interstellar object with such improbable chemical and physical properties also happen to choose the one trajectory that makes it easiest for us to see? Some wondered if gravitational focusing by Jupiter played a role. The giant planet's immense mass can bend passing objects toward the ecliptic, acting as a kind of lens. If 3I Atlas approached from above or below, Jupiter's field might have redirected it into a flatter path. But that mechanism only works for slow-moving debris. At interstellar speeds, Jupiter's influence is minimal. It would nudge the path by at most a degree, not flatten it entirely. So we're left with coincidence, or something more. Avi Loeb, the Harvard astrophysicist who spearheaded the Galileo project, put it cautiously. If an interstellar object enters precisely along the ecliptic and passes through the region where our observatories can detect it best, that doesn't prove intent. But it does warrant attention. His phrasing, doesn't prove intent, is deliberate. The implication, unspoken but palpable, is that intent is not out of the question. Still, not every anomaly needs a designer. Nature can produce alignment through complex cumulative effects, multiple gravitational tugs, coincidental deflections, even large-scale galactic flows. Yet the longer researchers analyse 3I Atlas's path, the less random it looks. Its inclination is ecliptic level, its speed is optimal, its perihelion is safe, its observational geometry is perfect, and its entry timing, during one of the sun's most active flare periods, puts it squarely in the crossfire of solar energy. If this were an experiment, the setup couldn't be more precise. As one astronomer from ESA's heliophysics division said, half jokingly but not entirely unserious, If you wanted to test how an object reacts to maximum solar stress, you'd send it exactly where 3i Atlas went. The alignment raises another quieter issue: transparency. Because despite the object's ideal positioning, some of the missions that should have captured pristine, close-range data haven't released anything yet. High-resolution imaging from US observatories, the kind that could clarify these mysteries, remains conspicuously absent. Meanwhile, Europe's data flowed freely. By early November, nearly every major astronomical facility on Earth and in orbit had turned its attention to the object. The European Space Agency released imagery and photometric readings from the solar orbiter within 48 hours of perihelion. The Japanese Hinoda mission published solar wind interactions. Even smaller observatories like La Palma and Calar Alto uploaded calibrated spectra to public databases. Yet from the United States, the country operating the most capable instruments in the right place at the right time, silence. The Mars Reconnaissance Orbiter had the perfect vantage point. During perihelion, Mars lay roughly 70 million kilometers from 3 Atlas's trajectory, close enough that the HiRISE camera could, in theory, resolve coma structures at kilometer scale. Its infrared spectrometer could have detected the exact composition of the sunward jet. NASA acknowledged that the probe was aware of the event, then stopped talking. No images, no timelines, no acknowledgements since. The same goes for the Parker Solar Probe. Its orbit placed it well within line of sight during the CME that hit 3i Atlas. Parker's instruments are designed to record plasma interactions, exactly the kind that might explain the brightness surge. Yet the only official statement was a brief technical note: anomalous data recorded during CME event 2025-10-29 under calibration review. Nothing since. Then there's the James Webb Space Telescope. JWST's mid-infrared capabilities are unrivaled for detecting molecular signatures like CO2, CO, and complex organometallics. For a few short days, its field of regard overlapped perfectly with the object's coordinates. Astronomers expected at least low-resolution spectra. Instead, Webb's public database lists a target of opportunity placeholder with no attached file. Requests for clarification received the same answer: data under proprietary review. That phrase, proprietary review, isn't unusual in research, but the timing raised eyebrows. ESA missions published within days. NASA's data, months later, remain embargoed. To the community, it looked like selective transparency. Inside professional circles, whispers began. Were the datasets corrupted? Did the instruments saturate during the flare? Or did the readings show something that agencies aren't prepared to interpret publicly? The speculation deepened when a group of independent analysts cross-referenced ESA's open telemetry with NASA's listed observation windows. They found overlapping timestamps, identical plasma disturbances recorded by both the solar orbiter and the Parker probe. ESA's public data clearly shows a coherent wave pattern at Surftorn 8 AU, corresponding to 3i Atlas's position. Parker's contemporaneous dataset, by contrast, contains a conspicuous blank, a 42-minute dropout labelled Instrument Safe Mode. For most spacecraft, safe mode means sensors were overwhelmed by radiation, glare, or signal overload. If the CME was intense enough, that would make sense. But the solar orbiter, exposed to the same flare, stayed online the entire time. Some began to suspect deliberate redaction. Within a week, posts appeared on internal astrophysics forums noting that the NASA Planetary Data System had delayed several scheduled uploads referencing 3i Atlas. No explanations, no cancellations, just quiet postponements. Scientists who requested the raw telemetry under data sharing agreements received polite deferrals. Processing continues. In contrast, the European Space Agency and Japanese missions shared everything, even messy, unfiltered readings. Their openness only highlighted the absence elsewhere. What's missing isn't just pictures, it's clarity. High-resolution imaging would confirm whether the anti-solar jet truly extended toward the sun or was an optical alignment illusion. Infrared spectra could validate the nickel without iron signature beyond doubt. Magnetometer logs might settle the debate about induced fields. Without them, the object's anomalies remain suspended between theory and rumour. When data silence meets data noise, conspiracy inevitably fills the gap. Online forums began speculating wildly: claims of engineered object, solar probe interference, even intentional blackout, most of it noise. But buried among the noise were legitimate questions from credentialed scientists who found themselves locked out of information they normally would access. Dr. Linnea Korhonen, a plasma physicist from Finland's Space Research Institute, expressed her frustration in an open letter. It is not credible that every sensor designed for heliophysics went blind at the same time, while European and Asian instruments continued recording. If something unexpected occurred, the scientific response should be transparency, not silence. Her words resonated because they reflected a deeper discomfort, that the object was no longer treated as a curiosity, but as a sensitive event. There are precedents. In 2020, when Interstellar Object 2I Borisov disintegrated, some data from US military optical assets were withheld due to national space surveillance protocols. The reasoning was partly technical. Certain telescopes are classified. But 3I Atlas was observed by civilian missions. No such excuse fits easily. Some insiders hint that the issue may involve spectral contamination. One rumour claims that the JWST readings contained unidentified emission lines overlapping with artificial satellite telemetry, frequencies near those used for communication lasers. If that's true, the data could appear artificially engineered simply because of coincidental interference. Until verified, NASA might be withholding to prevent public misinterpretation. Another possibility is more mundane but equally worrying. The instruments recorded phenomena outside their calibration range, data so anomalous that scientists can't yet model it confidently. Releasing it prematurely could fuel speculation, so they wait. But waiting breeds mistrust. Every day without disclosure adds weight to the notion that 3I Atlas revealed something beyond conventional physics, perhaps electromagnetic behavior or spectral properties too uncomfortable to announce without peer review. The narrative gains traction precisely because no one's contradicting it. In one sense, the silence is understandable. Extraordinary data require extraordinary scrutiny. Calibration errors, cosmic rays, solar reflections, all can mimic miracles. Yet the longer the delay, the more it feels like containment rather than caution. And in that vacuum, theories multiply. The simplest says that NASA's instruments detected energy frequencies inconsistent with natural plasma emissions, narrow band, possibly modulated signals. Another says the magnetic field oscillations matched artificial harmonics. Both sound implausible, but without public data they can't be disproven. Meanwhile, ESA's openness continues to show nothing explicitly technological, just highly unusual natural physics. Yet even their scientists admit confusion. Their latest bulletin concluded diplomatically. The object exhibits coupling between solar plasma and compositional materials not represented in known cometary analogues. The mechanism remains unidentified. That's bureaucratic language for we have no idea what's happening, and that lack of clarity is pushing 3I Atlas from scientific anomaly toward paradigm challenge. Because each unanswered question, the nickel emission, the polarization, the ecliptic path, now the data blackout, compounds the sense that this is not simply another comet story. The scientific community now finds itself split, not just on interpretation but on access. On one side are those demanding full transparency, on the other, agencies citing caution, calibration, and classification. Between them lies a void as wide as interstellar space, and while scientists argue over what's missing, theorists have begun filling the silence with explanations that sound like science fiction but might not be. By mid-November, the object was already moving outward, fading from the solar glare, but in its wake, it left something more enduring than plasma trails, a scientific standoff. What exactly had we just witnessed? 3 main theories have emerged, each backed by credible scientists, each mutually incompatible, and each equally unsettling in its own way. The most conservative explanation treats 3I Atlas as a kind of accidental aurora, a natural light show caused by solar wind bombardment. In this view, the October 29th flare didn't just heat the comet, it electrified it. Charged particles from the CME slammed into the object's nickel-rich surface, exciting electrons the way they do in Earth's upper atmosphere. As those electrons returned to lower energy states, they emitted light, explaining the anomalous brightness spike. This model accounts for several anomalies at once: the delayed glow after the flare, the narrow emission bands, even the shrinking coma. A localized magnetic sheath could, in principle, confine ionized gases, compressing the coma and creating a phosphorescent envelope. Yet even its proponents admit the math strains credibility. For auroral processes to generate that much luminosity, the induced current would have to exceed 10 million amperes, far greater than anything a kilometre-scale nucleus could sustain without tearing apart. And auroras require a magnetosphere. How would an interstellar chunk of ice and rock generate one strong enough to rival a small moon? Still, supporters point to the CME alignment and the anti-solar jet as evidence that electromagnetic forces dominated this event. They call it a heliospheric lightning strike, a 1 in a billion accident. Then there's the chemical school, those who argue that 3I Atlas isn't behaving electrically but chemically. They see the object as a laboratory of alien compounds, reacting under solar heat in ways never before observed. In their scenario, the combination of carbon dioxide, trace carbon monoxide, and exposed nickel grains created a self-sustaining chain of reactions. Solar UV light acted as the catalyst, forming transient organometallic molecules, especially nickel carbonyl NiCO4. When these molecules broke apart, they released photons, producing the narrow emission lines mistaken for electrical excitation. This theory explains the nickel without iron mystery elegantly. Nickel can form volatile carbonyls. Iron cannot, at least not under those pressures. It also explains the stability of the brightness curve. Chemical oscillations can persist for hours as reactive surfaces cycle between bonding and dissociation. But the theory's elegance is also its weakness. The required chemistry has only ever been demonstrated in laboratories under precise temperature and pressure conditions. The interstellar vacuum doesn't provide that. And to sustain light emission visible across astronomical units, the reaction rate would have to involve millions of tons of material reacting simultaneously, an implausible scale for surface catalysis. Still, the chemistry camp has found support among planetary scientists who prefer molecules over magnetism. It's alien, but not unnatural, one researcher at CNRS put it. A different star, a different chemistry, that's enough. And then there's the outlier theory, the one most scientists won't say aloud in conferences but will quietly discuss after hours. It suggests that 3I Atlas isn't merely reacting to solar forces, it's using them. The idea originated from an analysis of magnetic field data by an independent team at the University of Padua. They noticed that the oscillations around 3I Atlas during the flare followed a repeating harmonic, a periodicity of roughly 1.4 Hz. That frequency recurred across multiple instruments and persisted longer than the CME's natural pulse. In simple terms, something near the object seemed to be modulating the plasma environment. Theorists dubbed it the engine model. In their interpretation, 3I Atlas acts as an electrodynamic body, perhaps containing conductive veins or cavities, that can channel solar energy through internal induction. When struck by plasma, it resonates, converting electrical currents into mechanical or radiative energy. The anti-solar jet, under this model, was not random outgassing but the visible exhaust of that conversion. No one suggests it's artificial in the human sense, but the mechanism itself borders on engineered physics, an object optimized through compositional geometry to interact with a star's magnetic field. Skeptics call it fantasy. The energy balance doesn't fit. The efficiency would have to be enormous, but proponents counter that if 3I Atlas originated in a magnetically rich stellar environment, natural selection of materials could have produced exactly such properties. Not intelligence, just physics pushed to its most efficient form. Whatever the truth, the object's measured stability supports the idea that it manages energy better than ordinary comets. It didn't fragment, overheat, or spin out of control. It absorbed, reacted, and recovered, like a system in equilibrium. Each hypothesis explains part of the picture. None explains it all. The auroral model accounts for brightness, but not chemistry. The chemical model explains spectra, but not magnetism. The engine model explains coherence, but stretches plausibility. And then there's the elephant in the room. None of these models account for the trajectory, the perfect ecliptic alignment, the survivable perihelion, the timely CME strike. That chain of coincidences makes even the most skeptical minds pause. When asked which theory he found most convincing, an ESA physicist reportedly smiled and said, "Whichever one doesn't make me sound insane." A few researchers now advocate a hybrid interpretation. They argue that 3I Atlas's behaviour may arise from interactions between all three domains, plasma, chemistry, and structure. Under extreme radiation, conductive nickel grains could form transient electrical networks across the surface, guiding plasma discharges that in turn trigger chemical reactions in the CO2-rich crust. The object, in this view, becomes a self-coupled system, a natural plasma chemical reactor operating on an interstellar timescale. That synthesis model has gained quiet traction because it avoids absolutes. It doesn't require intelligence, but it doesn't deny organization. It allows 3i Atlas to be natural and extraordinary at once, a relic of cosmic processes that mimic purpose through physics alone. Still, one question overshadows all of them. Why now? The sun's activity, the ecliptic alignment, the observational window, all coincided perfectly to make this event visible. If the same object had arrived a year earlier or later, it would have passed unnoticed behind the sun's glare. Nature may be random, but this felt staged, which is why some scientists are already looking ahead to what happens when 3i Atlas re-emerges from behind the sun in November and December. Because whatever its true nature, the next round of observations will determine whether these anomalies persist or vanish with the object into deep space. When 3i Atlas slipped behind the sun in early November, the world's telescopes fell silent. For weeks, no instrument on Earth could see it. It was hidden within the blinding halo of the solar disk, unreachable to even the most sensitive detectors. But the silence didn't last long. As mid-November approached and the geometry began to shift, observatories prepared for what they called the November window, the first post-perihelion glimpse of the interstellar visitor after its encounter with the sun. It was the moment of truth. Either the object would reappear as expected, dim and cooling, or it would emerge changed, altered by whatever had happened at perihelion. By November 17th, preliminary recovery attempts began. The Lowell Observatory in Arizona was the first to report a faint detection near its predicted coordinates. The brightness was lower than expected, but oddly stable. Within days, the European Southern Observatory confirmed the sighting, followed by independent verification from Chile and South Africa. 3i Atlas had survived. It was intact, coherent, and still exhibiting mild photometric anomalies. The initial relief quickly turned to curiosity. Comets after perihelion typically lose brightness rapidly as they move away from solar heat, but 3i Atlas held its magnitude almost constant for days. It wasn't fading according to thermodynamic models. Instead, its light curve showed subtle pulsations, small rhythmic variations roughly every 7 hours, matching its rotational period. Each pulse was accompanied by a slight spectral shift towards shorter wavelengths, a sign of either thermal flickering or residual plasma activity. Whatever process had powered its outburst near the sun was not completely gone. Observers noticed something else. The coma hadn't returned to its pre-perihelion shape. It remained compact, denser than any post-perihelion coma on record. The dust halo glowed faintly cyan, suggesting the presence of ionized CO2 or CN, carbon-nitrogen radicals produced under continued radiation. But at that distance, 1.6 astronomical units, and increasing, the sun's energy should no longer sustain ionization at that level. It meant that 3i Atlas still retained an internal charge or reactive surface chemistry capable of self-luminescence. Some described it as a lingering afterglow, others weren't so sure. Data from ESA's solar orbiter hinted that the region of space trailing the object was magnetically disturbed. Weak plasma waves persisted days after the body had passed through, as if it left a wake in the solar wind. That kind of magnetic echo has been seen around large asteroids, but never around a body this small. It implies residual electromagnetic coupling, as though 3i Atlas continued to interact with the solar environment long after direct exposure. When the Hubble Space Telescope finally captured high-resolution imagery, analysts noticed something disquieting. The coma's inner core was slightly elongated, not spherical, not diffuse, but stretched along the same axis as its anti-solar jet from weeks earlier. Even after the outgassing had ceased, the structure remained imprinted, as if frozen mid-discharge. The geometry suggested that whatever mechanism produced the sunward jet had left a lasting mark on the object's shape or field. At this point, the narrative within the scientific community split into two directions. The cautious voices insisted that the anomalies would fade as the object moved farther out. They argued that the apparent pulsations and magnetic wake could be transient residues of ionized gas dispersing slowly in the solar wind, but others suspected continuity, that 3i Atlas might carry a persistent energy system, still active but diminishing, like embers glowing long after a fire's collapse. Astronomers at Calar Alto Observatory noticed that the 7-hour periodicity and brightness wasn't perfectly constant. The peaks gradually shifted, as if the object's rotation was decelerating slightly, a change of only a fraction of a second per cycle, but measurable. Under normal circumstances, outgassing causes spin-up, not slow down. The deceleration hinted at drag, perhaps magnetic, not mechanical. If the body was still interacting with surrounding plasma, it could be bleeding rotational energy into the field, like a dynamo winding down. Even the photometric data carried a strange coherence. Over a 2-week span, the colour indices barely fluctuated, suggesting that surface chemistry remained stable. No sign of fragmentation, no dust trails, no volatile flare-ups. The object seemed to have reached equilibrium, a silent, self-contained system drifting away from the sun, carrying its secrets intact. And yet the silence around it wasn't just visual. NASA's missions, which had gone quiet during perihelion, still hadn't released their datasets. The expectation was that after the solar conjunction ended, those observations would finally surface. They didn't. Only generic statements appeared, noting that data review continues and public release pending calibration. Weeks passed with no files. ESA, in contrast, began publishing their post-perihelion analyses. Their tone was cautious but telling. In a November 29th bulletin, they wrote, "The photometric persistence of 3i Atlas suggests surface or subsurface processes that are not yet fully characterized. Continued monitoring recommended. The wording was scientific understatement, for we have no idea why it's still glowing." By early December, when the object had reached nearly 2 astronomical units, its brightness finally began to wane, but not linearly. Instead of a gradual fade, it dimmed in steps, brief plateaus of stability followed by sharp drops. Each plateau lasted roughly 1 rotation. That pattern, repeated over several cycles, looked deliberate. Not controlled, perhaps, but governed by an underlying rhythm. It resembled a machine running out of power, each spin discharging the last reserves of stored energy before falling quiet again. And then, without warning, the spectral lines of nickel returned. Faint, almost ghost-like. Observatories in Hawaii and Chile both detected weak emission near 351 nanometers, the same wavelength that had dominated the flare event. The lines appeared during one rotation, vanished on the next, then reappeared briefly 3 days later. It was as if the object in its cooling state was flashing a signature, one last spectral heartbeat before slipping beyond reach. After that, the light stabilized at a faint but steady magnitude. The cyan tint faded to grey, the nickel lines disappeared, the wake dissipated. By December 10th, 3i Atlas was once again a silent traveller in deep space, indistinguishable from 1,000 other cold fragments orbiting the sun. But those who had followed it knew better. Something in those few weeks had rewritten what they thought possible for small bodies. The November window closed quietly. No explosion, no revelation, no catastrophe. Just a distant flicker fading into the void. Yet for many scientists the unease remained, because if the anomalies had ended naturally, the data should have confirmed that. It didn't. The silence persisted. The withheld spectra, the missing telemetry, the unexplained harmonics, all unresolved. For the first time in decades, a celestial event had generated more questions than answers, and the answers themselves were locked behind competing narratives. Some called it the most important cometary encounter of the century. Others called it an embarrassment of confusion. But among the few who had seen the full data, the reaction was quieter, a sense that this object, whatever it was, had interacted with the sun in a way that revealed something deeper about both. Because perhaps the story of 3i Atlas isn't about what it was, but about what it showed, that the boundaries between matter and energy, chemistry and plasma, natural and intentional, may not be as clear as we once believed. The scientific community now faces a question it rarely asks aloud. When an anomaly refuses to fit the model, is it the object that's strange, or the model that's incomplete? By late December, the tracking logs thinned out. The world's observatories turned their gaze back to safer mysteries, distant quasars, predictable asteroids, exoplanets that followed their orbits like clockwork. 3i Atlas had slipped beyond 2.5 astronomical units, its reflected sunlight now too weak to resolve detail. On paper, it was just another receding object in a growing catalogue of interstellar debris. But for those who had followed every faint pulse of its light, that sterile description felt dishonest. What they had witnessed was not debris. It was defiance. A small, silent fragment that refused to behave as physics said it should. No one can yet explain how an object could brighten under radiation it should not have survived, or emit nickel lines without iron, or twist polarized light into impossible directions. No one can reconcile how it shrank its own coma while glowing brighter, or why it travelled perfectly along the ecliptic, as if placed on the only trajectory that would guarantee our attention. Every explanation offered, electromagnetic, chemical, magnetic, explains something but not everything. The puzzle holds because the pieces do not quite fit. In the months that followed, committees formed and disbanded. The data that should have settled the debate never arrived. Some claimed the instruments had glitched, others whispered that the readings had been too strange to release. The truth, if there is one, sits in encrypted archives, waiting for clearance or courage. Meanwhile, the published models diverge further each week. Some insist on plasma resonance, others invoke carbonyl chemistry or deep interstellar alteration. A few, quietly, suggest intentional design, though they phrase it in euphemisms like non-random coherence or directed alignment. And somewhere beyond Mars the object itself drifts on, cooling, fading, indifferent to what we make of it. Its orbit is open, it will never return. In a few years it will slip beyond the heliopause and vanish back into interstellar darkness, carrying whatever secret mechanism kept it alive through the sun's fury. When it's gone, only its data, fragmented, incomplete, contested, will remain. Yet something deeper endures, because every once in a while, the universe drops a reminder that our understanding is provisional, that even after centuries of observation, a single visitor can arrive and quietly dismantle our certainties. 3i Atlas did not rewrite the laws of physics, but it exposed the seams between them, those thin cracks where mystery still lives. It showed that an object can act like matter and plasma and machine all at once, and that maybe those distinctions were never as clean as we thought. In time, the story of 3i Atlas will probably be reduced to equations and citations, its strangeness normalized by new theories. But the memory will remain of that brief moment when the sky glowed brighter than it should have, and scientists across the world stared at their monitors, seeing something that didn't belong there, yet undeniably was. Maybe that's how discovery always feels at first, not revelation, but discomfort. Not proof, but the quiet realization that the cosmos is still stranger than we are willing to admit. And somewhere, far beyond the sun's reach, that light, the impossible glow that started it all, is still travelling outward, unchanged, racing through the dark.